Alrighty, folks, welcome to module number 6. We are going to go ahead and get started here. So let me go ahead and navigate us down here to computer graphics and to module number 6. So we're going to be talking about a few short topics today with modeling things in perspective, so modifying our shaders and seeing how to do that. And we're going to talk a little bit about debugging and then give you a few tasks for labs. So lab 6 is going to be another two-parter. Okay, so let's go ahead and dive in here. And let's see what we got for today. So of course, always some readings to do, your in-class activity, but let's jump into the slides. So for today, a little pre-class warm-up for us, a fun one here. And it's in the spirit of our homework, which has been released. That's assignment 3, where you're going to be doing some rendering of wireframe models, as well as filled in. It's actually a 1 or a 2-liner to flip between the filled in or wireframe mode. So I'll let you do a quick Google search on that. But in that spirit, wireframe drawings have actually been done of objects like this chalice here since way back in 1450. So this is by Paulo, and I won't pronounce the last name, but kind of a cool rendering here of this idea. So if we go ahead and hop into our monorepo for assignment number 3, in part 1, you will see that you will be rendering a wireframe of a bunny as well as a filled in version. So one or the other, you'll toggle with the W key and be able to render this bunny here, which is known as the Stanford bunny. So that'll be part 1 of your assignment. Part 2, you'll actually get to have a little bit of fun here and do a little bit of modeling. So here's a quick object that I created. You can create whatever you want, and you don't have to spend a whole lot of time on this. I would say an hour or 2 is fine. I state here no more than 4 hours on this. Anything that you make is just to sort of get you into learning how to create 3D models. I think that's also an important skill. So that's the homework, so you can practice around in Blender or whatever tool you want here. Okay, so anyway, with that in mind, just a fun warm-up and a little preview at our assignment 3. And with that said, some of these foundational things that we're working on really come from the foundations of computer graphics, which gave me the idea to highlight this pioneer of computer graphics, Andreas van Dam, or Andy van Dam, one of the co-founders of SIGGRAPH, the conference I mentioned previously. And he's also known for writing what's considered sort of the Bible of computer graphics amongst all the textbooks, but it's called Computer Graphics here. You can see sort of the Ratatouille character here. But he is one of the main authors. Him and John Hughes had written the original version and since have written other versions of it. So it's pretty cool. And Professor Van Dam has been teaching at Brown since at least, I believe, the 60s or so. I think he got his PhD at UPenn. And was the second person to get a PhD in computer science there. But so even after all these years, he's still innovating on graphics, which is super, super cool. So anyway, here we are recording. So I briefly mentioned assignment 3 and that had been released here. But what I also want to push forward here is that the final project has also been released. So I'm going to go ahead and click on this. It's another repository that you'll create. I'll create a team. The instructors team, don't join this team here. But the idea for the final project is you get to work on pretty much anything that you want. It's a pretty liberal assignment here. So let's go ahead and take a look here. And the goal of the final project is going to be to create something, to the equivalent of a difficulty of an assignment and push a little bit beyond that. And really this is going to be a portfolio piece for your computer graphics work here. So you can read a little bit here about my expectations and so on. You have a lot of freedom as to what technology you use. If you're excited about something else, here's some sort of project ideas that I would want you to sort of take a little bit of time to look at these and think about them. And then just how to sort of strategize. You can do it in a team up to 2. About 75% or so people usually do this individually, and in part because it is part of your personal portfolio, so it's something that you want to work on. In the short summer semester, I might also recommend that, but it's up to you if you're taking this with a friend or want help facilitating. This is a team project, you're more than welcome to. So anyway, the main deliverables of this project is a project that I can build in the core staff with just running Python, build .py to execute your project. And you'll have a deliverable, of course, of your source code, but also a little 2 to 3 minute YouTube video highlighting what your project is. So sort of talking about the an important accomplishment that you did. Maybe it was an algorithm, a graphics technique, something that you built. You're teaching in this video and showing off your project. So of course, there's going to be this sort of visual component of what you've built, and highlighting the sort of algorithm of what you did. Okay, so I want you to highlight again in some video at least one technical achievement. Maybe you made a really cool data structure, a piece of the code that was tricky. Just something to sort of show off on your portfolio. And I give a few examples from previous years here that you can read through, and just some notes on my thoughts about what I liked or didn't like about them. And I'd encourage you to be as ambitious as you like here. Okay, so that'll be your final project. I'll do some reminders throughout the semester, but you'll just edit this README with a link to your YouTube video, or it can be a public Dropbox link or something, just something that we can get a look at. And then as well as a few screenshots of your project here. Okay, and these are the screenshots I'll try to use for our sort of end of year presentation. That's usually fun. So just a note on that. So the final project is out. You can click on it on this link, or if you go to the course homepage, if I make this a little bit smaller, you can click on the final project repository here. If you are interested in forming a team, there's a spreadsheet here you can click on, and it will bring up some folks here. I'll delete the previous folks, but you can see the link here. Okay, so that'll be the idea. Okay, so, and then there are previous year projects here, and then some more ideas on the final project if you'd like to take a look there. Okay, so that's just a little bit on the logistics. I'm also going to likely be pushing out assignment 4 relatively soon, again, just to get a little bit of a head start for folks who want to work on the long weekend if you're watching this on Friday. All right, so last time we talked about our first shape. We learned what a vertex buffer is, so our sort of great ideas in computer graphics, a way to sort of ship information, in this case, vertex buffer, so vertex information to the GPU. And then we drew some objects with GL draw arrays. Okay, that was part 1 of your lab. And then later on, you learned how to do this with something called an index buffer. So this idea that if we have a bunch of vertices that are shared, we may want to reuse those. So we can do that by just indexing into our vertex buffer in X, Y, and Z vertex and reusing it again. So it's a little bit more efficient as far as using the index buffer. And in fact, this is how a lot of geometry is going to be stored. So for instance, for assignment 3, you're implementing an object file loader. So this sort of makes sense that you would just be indexing into the text file with all the vertex information. Okay, and while you're doing this, you also got a little bit of experience with shaders, whether you're reading through them in the lab or just kind of getting a high-level idea that there are these separate programs that we're writing that tell us what to do with our vertices in the graphics pipeline, or how to shade them in. Okay, that's the idea with these shaders. And they're very powerful because they're programmable. So we can have multiple vertex shaders in our program, or multiple fragment shaders, and sort of have separate pipelines and different ways for objects to be drawn or shaded in. Okay, so for today's goal, it's to just push us a little bit further here. And I'm going to talk about just a debugging technique first for finding errors in OpenGL. We'll add some color to our triangle and try to understand our shaders a little bit better. And then finally perform a little transformation with our camera and introduce the math library that we'll be using. Okay, so let's talk about the first topic here, OpenGL errors. And they typically form in the, you might have come up with some sentence here that says, hey, nothing's showing up. So if you've launched your OpenGL program and it just looks like this when you're expecting a triangle or some shape or figure here, it can be a little bit difficult to detect errors in OpenGL sometimes. Okay. So, my question to the audience is, what do you think are the reasons that this could happen? And I'll give you a moment to pause the video and think about this. Go ahead. So if you've paused the video and taken a moment to think about, why wouldn't your geometry be showing up in the screen here? Well, there's a couple common OpenGL errors that occur. So maybe you just forgot to send data to the GPU. Maybe your triangles are reversed. Remember we talked about the winding order. They have to be counterclockwise by default. Maybe you have an error in the shader, in which case our infrastructure will print out the error that occurred. So you can try this, right, in your Vertex shader, omit a semicolon somewhere, and you can see that the error print out in your console. Maybe you forgot to call GL clear, or maybe you're calling GL clear in the wrong spot. And by wrong spot, I've added a note meaning right after you draw your geometry, you just clear the screen. Okay, that would make your screen go blank. And maybe it could be an SDL error. If there's some configuration missing or you didn't initialize the graphics subsystem or so on. And there's a bunch of other common mistakes here that could occur. So you can kind of use this as a reference here. I guess they've added over time, the common mistakes here, as well as common mistakes in shaders and so on. So this can be quite helpful here, okay, for building up your expertise. So that's one thing to know, but we actually do have some tools. It's enough to just know what the common errors are, and as you gain experience, you'll be able to anticipate maybe what's gone wrong. But OpenGL comes with a basic primitive error handling function. Okay, and this is sort of, since it's a C API, this is sort of the C programmer way of doing things. But all the OpenGL functions have some, or most I should say, have some sort of return code that they give. Okay, so remember OpenGL is this giant state machine that's keeping track of what's going on. And you can make this function call glGetError at different points in your program, and it'll say, or report if some error occurred. Okay, so here's an example of one of those error messages where you have some illegal input value. Okay, so let's go ahead and look at this in the code, and I'll recreate an example here to show how to use this. But in our code for today, in most of our labs, I'll also provide this, and you can always add it back in. But I've added a little error handling function that you can use in one call. It's called GL clear error states. And what this does is it says, okay, check to see if there's any errors that occurred. Okay. And then I have another function called GL check error, which will take in the function that we're currently executing in the line, and then it'll report what the error is that we're checking for here. Okay, so how this is used, and it'll make sense. I'll show you a use case of it. You have the implementation given, but we can wrap this in what's called a macro in C++. So C++, remember, anything that begins with a pound symbol means the preprocessor is going to take this and do a textual replacement. So I've defined this thing called GL call. It takes an argument x, and then it's going to substitute whatever we wrap with GL call in parentheses. So maybe some OpenGL function called GL clear, GL draw, or something like that. And then before it, it's going to put GL clear error states and say, okay, there's no errors. Whatever our command is, our OpenGL command, and then check if an error occurred. And then it'll report, if I put the pound sign in front of it, as a string, the line number at which the error occurred. Okay? So this is the idea again. So this is our macro. X is whatever X is our OpenGL command. We're going to call this function to clear the errors, and X is the original function I want to check errors for, and then we'll print out the error message. Okay, and try to get some information. So here's an example of some code you may accidentally write. It says GL draw elements, GL triangles. Okay, we want to draw 6, the indices, so that seems right. And then we want to figure out what's the type here of our indices. So we put GL, okay, it's an integer, and then any offset or anything else here. Well, if you don't notice the problem, what we can do is actually just wrap this function with the GL call that we have here. So some OpenGL call here, and that's going to thus give us a little bit of information here. Okay, so let's go ahead and do that. And if we wrap this with GL call, we'll actually get some feedback back. And this is the feedback we get. OpenGL error 1280, which happens to be an invalid enum. Okay, and I'll run through this in a moment just so you can see what the error is. And it's highlighting that one of the values that we passed in here is illegal. Okay, so the indices actually need to be unsigned instead of integers. Okay, so this is our solution for how we fix it. Let's actually run through it in our code. All right, so let me go ahead and just try to recreate this here by going back, and I'm going to just download the repository here and make a change to the lab code for today, lab 6. So I'll just clone a fresh copy of that repository, and I'm just going to make this an example. Here, git clone, enter credentials as usual, and give that just a moment to wrap up. All right, so we're going to go into lab directory number 6. And as mentioned, this is going to be a two-parter here. So there's going to be two parts to the lab. The first part is using the, well, rather just learning a little bit about the GLM library to get you used to that and how it plays its role in the graphics programming that we're going to be doing. But I want to go ahead and just jump into part 2 here. And let me make this a little bit bigger just so folks can see what's going on, or a lot bigger in this case. So what I want to do here is just show you the error handling code. So it's in the source directory and in the STL graphics program header. So it's at the top of the program that we have our code here. And these functions have otherwise been defined here for us. So you don't have to really do anything as far as modifying the program here. Okay, so let's go ahead and find that GL draw elements function. And you can see that I've wrapped this GL function here with GL call. So here's GL, and then the starting and the ending parentheses that have been highlighted here. So if you, for example, are trying to remember, what the arguments are of GL draw elements, so let's use docs.gl to do that. GL draw elements, and most of us are in OpenGL version 3 or 4, so whichever version you're using. You'll notice that the arguments are, well, an enum, a size, another enum, and then your vertices here. So if we look at, or rather the offsets here, if there is any, which we don't have. So here's an enum here where we could have something like GL underscore triangles or GL underscore lines, or unsigned int, for example. And if you can't remember these, the mode, for instance, will tell you what the valid arguments are here. And enums, if you're not familiar with, are just enumerations or just counting, essentially from 0 to however many items you have in a collection here, and they can be named. You'll notice for the third argument, the type is unsigned byte, unsigned short, or unsigned int. Those are the valid ones. And it makes sense that they're unsigned because they have to be positive values here for the type of data that we're working with. So if we accidentally put something in here, like unsigned int, I'll go ahead and save this, and we'll go ahead and run it. We will get a little error message here. And oops, it looks like my include path is a little bit off here. So I will go ahead and modify that because we are on Linux here. So I'll make sure this is prepared for your homework so you won't have that issue. So let's go ahead and just run this lab, and it's going to begin the initialization, and you're going to see the sort of fateful empty or gray screen here because we have some error here, and it says OpenGL. It gives us an error number, and then, well, it's giving us an error around GL draw elements here. That's the thing that we've wrapped, and it gives us the line number 265. So that's right here where we have GL call. So this is going to be our basic error handling. Now, some folks will, if their program's not working, a strategy is just to wrap every one of their GL calls, so anything that begins with GL, with this function. And that's perfectly fine for this course. We can talk about how to cleverly turn on and off error handling, but for the purpose of this course, just wrapping everything in GL call if you run into a problem is totally fine, and then seeing if you get the OpenGL error. So let's go back here, fix the error, recompile our program, rerun it, and then you should see, at least something on your screen. In this case, we just start out with a black triangle, and we will work on coloring that triangle in. So anyway, that's how to use or do a little bit of debugging with OpenGL with the built-in error calls. Okay. So I want to talk just a little bit about this idea, or some of the ideas here in our OpenGL code. It's that, well, we're using this macro, and depending on what school of thought you come from or what you read on the internet, people are going to say, oh, this is really bad, Mike. That's sort of the internet consensus. But the reality is, most of this work it's fine, if used in the right place. And this is just a general programming thing that I want to teach folks here. So I'll come into the screen to give you some my sage wisdom, I guess, here, that, languages have various features that you can use. So we're in C++ in this class, and pretty much every feature can be used for good or for bad. And in this case, I think this is a fine feature. It's how we have to work with OpenGL to do a little bit of debugging. So we're going to do our best with this feature here. And it's just something to keep in mind when you see very strong opinions on the internet about features. Sometimes they're good, sometimes they're bad. Weigh the trade-offs. In this case, it's going to help us solve a problem that we care about. So anyways, with that, folks have sort of thought about this and said, well, this is difficult, and using these macros and so on, and we wish we had more functions. But for those folks who have the hardware to support OpenGL 4, you're welcome to use this other feature. So it took them a while, but they finally added some other features into OpenGL. And I'm not blaming anyone, it just took a while for the hardware to support it. But there's something called a GL debug message callback. So let's go ahead and take a look at that here. GL debug message callback. And you'll see that this is only going to be for OpenGL 4 here. So again, you have to be on the latest and greatest, but basically you can have a function that is called if there is some error that occurs. Okay. So if we scroll down, I think there might be some examples. We can sort of Google an example on GL message callback here, how to use it. Usually the wiki page is pretty good, or whatever here. Stack Overflow might show an example of how to use it. But basically what this will do is if we define a function here, based off of some type of error that happens, you can have another function be called or log it, or sort of do something more interesting, collect the errors and report them to the user at the end of the program or whatever. So this is just an idea of something to know about. Again, here's sort of the message callback. Here's sort of the simple example. You enable it, and then you can have the GL debug message callback, which just says anytime an error occurs. So this is sort of the equivalent code without the macro that's saying what the type of the error is, and maybe the severity and some other things about it. Okay, so you could actually use this callback here that's provided, and you don't have to wrap all of your functions with GL call here. You just have defined this GL debug message callback. So what happens when there's an error in OpenGL? It calls this function, it prints this message out. That's the idea here if you're on OpenGL 4. Okay, so something to keep in mind here. And if you do want to use these features, go ahead and take you're free to modify our labs here by, let me just show you where in our SDL graphics program. About most people had OpenGL 4, so you can set the major version here to 4 if you want to use some of these more advanced features. 4.3, I believe, is the version we need. But most folks should be on 3.3, so that's our default. But you can upgrade yourself if you want some of these extra features. Okay, and in most cases, you don't have to make that manual change. SDL will just give you OpenGL 4.3. But if you want to explicitly do it, that's where to do it, so you know. Okay, so that's a little bit about error handling. I wanted to spend a little bit of time on that because it'll save you time later in your graphics programming career. So let's get to doing some graphic stuff and adding color to our triangles. So we can have something a little bit more beautiful than that previous triangle here, but with different colors here. Okay. And currently, the way that we've been drawing triangles is just one fixed color, right? We've been handling that by just choosing a fragment color in our fragment shader. So that's been how we did things in the previous lab, if you had a chance to complete that. We just sort of said, hey, we know there's going to be triangles and points, so when we rasterize them, just fill them in all the same color. But we can actually specify a color per vertex. And this can be important, one, just for the shading that we're going to do, but we can actually get some vertex colors that affect the lighting of our final model here. Okay, so just a reminder on color. Again, these are values between, in OpenGL, they're values between 0.0 and 1.0. Previously, when we worked with colors, they were between 0 and 255, but this is just 0.0 to 1.0. Okay, so how do we specify, though, the values per vertex, the x, or rather the r, g, and b values of each vertex? Because we were doing this previously with x, y, and z when we were just sending the vertex positions into our vertex shader. So again, just recall, here's what we were specifying in our vertex data previously, just the positions, x and y, or x, y, and z. Okay, so we had this whole thing where we were enabling a vertex attribute array and saying, okay, attribute 0, so 0 through however many you want, and we're going to pass in 3 things, x, y, and z. They're going to be floating data. Data's, is it normalized or not? How big is our data? How many vertices do we have? And so on. But we can actually repeat this for each of the attributes that we have. Okay, so now we want to send some more data, a second attribute, and that's going to be color. So if we want color, we add another attribute. That's it. So what our vertexes are going to look like, so here's vertex 1, it's going to have an x, y, z, and then an r, g, and b value. And then vertex 2 is going to have x, y, z, r, g, b. And we're essentially going to have what makes up one vertex is going to be 6 floats here. So 6 floats, they're each 4 bytes, so that's 24 bytes here. And to get to our next vertex, well, that's the next 24 bytes here. That's what the stride's defining here. Okay, and then our next vertex is the next 24 bytes. Okay, so you're going to use the code provided today to learn a little bit about this and add your attribute and think about what this offset is. But you can sort of draw this and specify the data in a vertex. And it's kind of cool. You can play around with this a little bit, or if you only need one color, or if you want to send other information, you can certainly do that. But this would be the idea. And usually we're sending X, Y, and Z, R, G, and B information for our vertices. Okay, so just looking at this a little bit, you're going to see in the vertex shader this sort of thing with a layout here. And you're going to see layout location 0. Well, that's our attribute 0. So that's referring to X, Y, and Z. And then you're going to see layout location 1. And that's the R, G, and B. Right, so we're laying out the data here in our shader. These first lines are sort of specifying, hey, what's the incoming data? You'll actually see another keyword here. It's called in. And it's a vec3 because we're reading in 3 things. 1, 2, 3. Our position's also a vector of 3 things. 1, 2, and 3. Okay, so we're explicitly just saying, hey, vertex shader, when we start you up per vertex, we're reading in information. The first vector of information is our position, and the next vector is our G and B information. Okay, so that's what these things are that you may have noticed at the start of our shaders. Okay, and then we have the output variable that goes into the fragment shader. So this is what our fragment shader is going to be reading in. So let me go ahead and show that on the fragment shader in the files here, part 2, shaders, and the fragment shader here. So the input this time is, well, whatever was coming out from our vertex shader. So this time, part of the layout for our fragment shader is just going to be reading in the color here. Okay, and then we're outputting color from our fragment shader, which is this value here. Okay, so that's just a little bit of a reminder on our pipeline and what some of these things are doing. Okay, so, and I referred to in here in the layout. Okay, so how does OpenGL interpolate color? Well, this is just an idea here that for these vertices here, I've specified their colors. This is one's blue, this one's red, and this one's green. And OpenGL is going to interpolate the color from one to the other. And it's just doing a very simple linear interpolation from blue to a red shade. So along this, as we're rasterizing, it'll fill in. It doesn't know exactly what to fill in the middle, but it's going to do, an average here for the distance from, well, whatever this vertex is. It'll get a little bit of that red shade. And whatever the distance is from here, and whatever the distance is from here, and that's how you get this sort of color palette here. This is known as interpolation, okay, and it's linearly done. Okay, so in order for OpenGL to run fast too, this sort of makes sense that it does this sort of cheap linear interpolation and that it can do it on the hardware. And it can do it relatively fast, just the red, green, and blue values, and just sort of interpolate for the colors in the middle. And it's a cheap effect, but it looks pretty nice when you're sort of blending between shades of colors. Now we're going to learn how to add more detail later, but this is a pretty nice effect for now, and it can also affect the lighting, which we'll also get into later. Okay, so let's start wrapping things up, and I just want to briefly talk a little bit about the camera setup here using GLM. So, it's enough that we have our triangle here if I go back, but it's kind of weird because it's upside down and it's really big. It's not in perspective. And we want to start rendering our 3D scenes in perspective, just like we were doing in our software rasterizers. So again, that means we need to transform our vertices in some way so that we can see what they, what our scene looks like in the real world. Have this perspective transformation where things that are further away appear smaller than things that are closer to the camera. Okay. And we're going to be using the GLM, or the OpenGL mathematics library, that's where the name GLM comes from, to help get us started with doing our transformations. Again, previously we were doing these in our great looking renderer with some primitive functions, multiply vector by matrix and some of these things, or init rotation and some of these, but we really want a expressive math library, and that's what GLM gives us. It's going to give us a whole bunch of mathematical functions to do this. Okay. So you'll notice that one error that I had previously in our build file. So let me just go ahead and show it in the build file. We've actually been doing this most of the build files. We've just been including it, just not using it. But in our third-party section here, in our mono repos, so I'll go ahead and show this here. In the common section, in third-party, I've actually already included GLM. Now you're welcome to upgrade the version, but this is a relatively recent version for us. Macs, I've had a little bit of issues, so I have an older version of GLM that I know works, so either one of these are fine, or you can update it if you want. We're using 0.997 here. So that's already been included here. And based off the version, you'll see the URL change. So I think it's 0.99 right now, but so you just want to match that there. Okay. But anyway, here's the documentation, the README here, which will define all the different types. And you can see there's a mat2 type, which is a 2x2 matrix, a DMAT type, which means it's a 2x2 matrix of doubles. So that's what the prefix is for the letter D here, and so on, in different dimensions that you would have. So it's going to have all these common 3x3 and 4x4 matrices that we would use in graphics. Okay, so overall, it's a very solid library if you're doing anything mathematical. For folks doing stuff even in machine learning, you might also be able to take advantage of this math library. Now, there's other specialized libraries for it, but this one will be good or similar. And of course, this is perfect for graphics. This is what it's built for. So the library itself is what's known as a header-only library. So we're just including the library and all of the implementation is inside of it. This is meant to make it easy. That's why it's been done this way. The other design decisions with this library, and why I've decided to just use this, in the past we've built our own, and that's an optional part of Lab 6 if you want to see. There's a hidden little old README if you want to build a matrix library yourself. I think it's a good exercise, but this one will keep us moving. And the math library also mimics the GLSL, the shading language that we're using when we're writing our shaders. So it's consistent. It's consistently named. So learning one helps reinforce the other. And I really like that. We could do that. There's other similar libraries like this GL matrix for JavaScript folks that follow the same idea. Okay, so it's in our library. So be sure to take a look here. Okay, so we have this math library and we can work with vectors, matrices, do all the sort of math things that we need to do, okay? Um, but now that we have this, we want to communicate some way from our CPU to our GPU these matrices, okay, or vectors or whatever mathematical operations that we're doing. Like if a user presses a key, how do we know to transform something on the GPU based off of the user input on the CPU? Okay, so how do we do this? Well, if you need a break, we'll get into it and I will show you how. All right, so if you've taken a break and are joining back with us, let's go ahead and talk about the last concept that I want to introduce, which is called a GL uniform. And this is our tool for communicating between the CPU and the GPU. Okay, so what is a uniform in OpenGL? Well, it's a global variable that's stored in the shader. And it's a constant variable, so we can't change it once it's been sent into the GPU. So within GLSL, whether it's the vertex shader or the fragment shader, you'll see some of these uniform variables. And this is how we can communicate every frame or sort of back and forth between OpenGL and the CPU, different values that we want to send it. Okay, so we have to, when we use GL uniform, send in a specific type into our shaders. So whether it's a float, 2 floats, 3 floats, or 4 floats, we have functions for doing that. And we'll send a specific location and the data here. So in this example here on the right, sending in 4 floats of information. So uniforms are sort of like our vertex attributes that we're sending in the instance of our vertex buffer is what I mean, where we're sending in that layout of XYZ RGB attributes. But again, uniforms are just constants that when we're passing in for our shader, it'll run on every vertex that's in the vertex buffer. And then we can change it the next frame that we are drawing if we want. Okay, so for the first part of the lab here, or rather where we're doing the OpenGL, or rendering a colored triangle, I'm going to suggest using attributes to do this because they're part of each vertex, the red, green, and blue colors. But uniforms, on the other hand, can change. So some functions of interest here in our C++ file. GL get uniform location and GL uniform for F. Okay? And in our shader, uniform. And we'll take a look in a moment. So what we're going to be doing to create perspective in our scenes is utilizing something known as the MVP matrix. So where we have vertex data and we want to transform things in perspective, right? So we're going to have our model that's moving our object into the world space, the view where we're viewing it from, how we're projecting it. We do other operations like clipping stuff that we can't see, doing a perspective divide so that we get everything into this window coordinate system, and then finally drawing our objects. So just a little reminder about that. But what we really care about, again, is the model view projection matrix, MVP. Model to world, again, transforming our object into world coordinates. World to view, where we are viewing our world. This is our perspective camera. So this is our perspective matrix here, or our view matrix, and where we want to position it. And then the view to projection, that does the squishing. Okay, so our model, our camera, and then our projection, MVP. Now it's important though to think about when we do matrix multiplication, what the order of these operations are going to be when you're applying the model, view, and projection matrix. So we're going to multiply them as the model times view times projection, or the projection times view times model. And that'll be something for you to think about and reason about for this lab. Okay, so I've given an example of setting up the uniforms in our camera here. So for instance, we will have a model transform matrix here. And this is just the identity matrix for our triangle, and I've pushed it back 1 unit on the z-axis. And then we use the handy GLM library to create our projection matrix. Set up the field of view, our aspect ratio, the near clipping plane, and far clipping plane. So how far can we see? And the model transform uniform is the next thing that we create. So what this is doing is it's setting up one of these uniforms that we're going to pass back and forth to our shader, and we're going to call this the model transform matrix. And then we have another one for our projection matrix, which is going to get this value of our projection matrix. Now, once we have created these values here, we need to populate them with an actual matrix. So we have GL uniform matrix 4FV. So this is a 4x4 matrix of floating values here. How do we refer to this uniform matrix? Well, by model transformation matrix uniform location, that's this. This is naming our sort of symbol. And you can sort of think of this as a handle into our GPU that's saying, hey, we want to create this integer here, almost like when we are doing the GL gen buffers and just generating something. So these two lines here are generating some memory or a way to address things in our GPU. And here's how we're populating those values in our GPU. So every time we call this function, it's going to send in the model transform matrix into our GPU for this name symbol model transform matrix, and the same for the projection matrix. Okay, and then once you have those there, you can figure out how to apply them in the fragment shader. So let me go ahead and bring up the fragment shader here. And it's just in our lab 6, part 2, our shaders, and then you can see, oops, we're working in the vertex shader, excuse me. Then you can see these uniforms, and you can see that they're named exactly as they are in our code here, okay? Lowercase m, capital T, capital M here, okay? So that's really important that they're named the same thing here, model transform matrix. All right, so a little bit of help for this and just getting used to or setting up the model view projection matrix. And it's just a few, this lab is really just 1 to 3 lines. You can do it in 1 line or roughly 3 lines to set up the correct perspective transform. That is figuring out where your model is in the world, how you're viewing it, so wherever your camera is. In this case, we don't really have a camera, so the view matrix is relatively simple. And the projection matrix that we're just generating from GLM, that says what our field of view is, the clipping, and so we don't have to specify that all ourselves, okay? And again, you'll be doing this in the vertex shader. Okay, so just to recap as we wind things down here, part 1 is going to be doing some exercises to get used to GLM and some C++ stuff. And part 2 is going to be to render your triangle in perspective. So you'll notice it's not just upside down anymore because our brain flips images. It's also viewed a little bit further away. It's pushed back 1 unit here. So this is what your a correct version of your lab can be. Now you can rotate it or do other things if you want to get a little bit creative, but this is an example of rendering things in perspective. All right, so if you encounter new commands today in the support code, you can always search docs.gl for those examples, as always. And here's our goals summarized in part 1 and part 2. And make sure to fill out the in-class activity. So this is a fun one, and we're starting to get into the depths of talking with our GPU from our CPU and working in the shaders. So super exciting stuff, and I hope you guys have fun with this one and enjoy the nice long weekend.